So then we start our last talk by Gary Froyland from the University of New South Wales, and he's going to talk about compound Poisson statistics for dynamical systems via spectral perturbation.
Thank you. Is this on? Yes. So thanks a lot. Thanks to the organizers for the invitation and the opportunity to speak. Thanks a lot to the local people. I've really enjoyed my time here, and also to the Amici. I've really enjoyed the conference so far. So this is joint work with Jason Atnip and Cecilia Gonzalez-Topman, who gave a talk on Tuesday, and Sandra Vallenti. And let me start with a simple example where you have a single deterministic map of the interval. So it's piecewise smooth, expanding, and it has an ACIM mu. And introduce in the domain some targets. So I'll have a sequence of targets. Maybe think of intervals or unions of intervals. And they're indexed by n. And as n goes to infinity, the size of these intervals decreases. Okay? And we want to know, in an orbit of length n, how frequently do you hit the target? And you can count this with this Birkhoff sum. So you start at some x, you iterate your map, and whenever you hit the target, then you pick up one of the indicators. And so you can define in this way a random variable z on the integers from 0 to n, and tells you how likely it is that you hit the target j times in an orbit of length n. And what we would like to do is ask the question, what happens as the targets shrink? So here I'm saying that the target size, according to mu, should shrink like t on n. So t is some number, some scale factor that you pick. And yeah, what happens in the n goes to infinity limit? So if you haven't seen this kind of thing before, then maybe it's useful to think of a really simplistic situation where you say, well, my map is expanding, it's chaotic, so maybe the event that I hit the target, maybe these events at different iterates are independent. Okay, so then I have Bernoulli events, and what am I doing? I'm trying to hit the target. I get n attempts, and each one has some success probability t on n, which is the measure of the target, and so then my Zn would be binomial. And then if I let my n go to infinity, then I would converge to Poisson with parameter t, so n times t on n. And already you can see why the scaling t on n is important, because in this simple case, if you didn't have t on n, you would get a limit of 0, or the limit doesn't exist. And in fact, this intuition is not bad. So coming back to the deterministic map, if you have your target, which is an interval, and it shrinks to a single point, and that single point is aperiodic for the map, then, in fact, your Zn is limiting to a simple Poisson with parameter t, so just like the simple-minded experiment. Okay, well, if you have a single map and you have intervals that contract to a single point, we covered here the aperiodic case, so the other case is the periodic case. So let's say you have intervals shrinking to a single point, and that point is periodic. So now you have a target, let's say some interval around your periodic point, and let's say you hit it, so you came nearby that periodic point, so then you have some greater than average likelihood that when you iterate r times, if r is the length of the orbit, then maybe you come back and come nearby again, because you're in this neighborhood of a periodic point. So you would expect some correlation between hitting now and r steps in the future and 2r steps in the future and so on. And you would not necessarily expect simple Poisson as a limiting distribution. And that's, in fact, correct. So what has been shown, and what we could show as a simple version of what I'm going to talk about today, is that the Zn converges to a geometric Poisson, or polar aptly. And the parameters are given by t, 1 minus alpha. So t, remember, is the scale factor. And the alpha here is the accumulated inverse derivative around the periodic orbit. Okay, so what does this look like? Well, it means that your z, your limiting distribution, is of this form, where the x's are IID and the n is Poisson distributed. So the n is distributed with parameter t1 minus alpha, and the x is IID geometric with parameter alpha. And one way to think about this is that the geometric x's are telling you when you hit once, how likely is it that you return and return and return before you go away? And that's related to the alpha. So the expansion away from the periodic point will, if you expand fast, then you would tend to return less, and if you expand less so, you tend to return more. And if you compare this idea of clustering with the previous slide, then on the previous slide we had a simple Poisson, and you could trivially write this simple Poisson as sum j is 1 to n of 1, and so there the cluster size would be 1. Okay. All right, well, I want to do this kind of thing, but for random dynamical systems. So I have a collection of maps, T omega, and I have some driving system, and the driving that we're thinking of is similar to what Cecilia talked about in her talk. So we just have ergodic driving. We have no hypotheses on mixing or decay in the base. And we're going to start with a random dynamical system that has, let's say, a thermodynamic formalism. So I need some well-defined statistics. And I'm going to assume that we have a random conformal measure, random equivariant functions phi, and you could put them together in the usual way to get a random invariant measure. And for the piecewise continuous case, this is not so straightforward to get, but in earlier work with the same set of authors, we have some conditions on the maps to guarantee that you have this random thermodynamic formalism. And the mu's are what we're going to use to set up the Zn distributions to do the hitting time statistics. Okay, so now we also have random targets, and we do a similar thing. We have now several fibers, right? So we have, this is the omega fiber, this is the sigma omega fiber, and so on. And on each fiber, you have a copy of whatever your domain is, and you put a different target on each fiber. So the H's are indexed by omega. They all decrease again at this 1 on n rate, and we can count the number of hits now along a sequence of targets using this counting function. So we have this random variable in x, and what we're doing is we start on the omega fiber at x in our domain. We check, did we hit the target at that fiber? Then we iterate with our current map to the next fiber. We check, did we hit the target there? We update our base, and on and on and on, randomly, like this. So this will count the number of times your random orbit hits a random sequence of targets in an orbit of length n. And then we make these z, so previously I had zn, now I have z omega n. So this is doing just what is in bold here. And we want to now take the n to infinity limit and ask what is this limiting z in the random case. All right. So now I have a couple of slides talking about connections with extreme values. So sorry if you are an expert in this and you've seen this before, but if you haven't, then maybe it's new. So there's a standard connection between hitting targets and extreme value theory. So you have an observation function, h, and this might be something like temperature, and you want to know when does the temperature get very hot, when is it extreme. And in our case, the observation functions themselves will depend on the base configuration, omega. And so what you do is you make a series of observations. You start at some x, you run your random dynamics at each fiber, you make your random observation, and you generate a random sequence of real numbers, which are the observations. And then we will say that on the jth, sigma jth omega fiber, you had an extreme event if the observation at the point in your domain exceeds some number z. So you have these thresholds. So if this is like temperature, then this is some reference temperature, and you exceeded the reference temperature and you saw an extreme. And then a natural thing to do is to say, well, the parts of the domain where I observe these extremes, they can be my targets. That's one way to generate targets. So you would define your target as the points in phase space where you have your extreme event. Okay. All right. Okay, so in an earlier paper, in basically the same setup that I'm talking about today, we developed a random extreme value theory, and I guess I'll say a little about that here, but what I'm talking about today is beyond that to talk about the hitting time distributions. And yeah, now I spend maybe 1 minute saying, why do we bother with all these omegas everywhere? So why would you want random observation functions? Well, if you're in a situation where your observation apparatus depends somehow on the underlying configuration, maybe it has a bias or some other dependence, then this allows you to have your observation depending on your underlying system configuration. Why would you want to have random thresholds? Well, coming back to the temperature example, let's say you're a climatologist and omega is tracking the seasons of the year, and you want to know when is the ocean temperature warmer than, say, 2 degrees warmer than it should be for a certain time of year. So obviously the water temperature is warmer in the summer than the winter, but as a climate scientist, you don't care about whether it's winter or summer. You want to see whether it's 2 degrees warmer than it should be for a certain time of year. And so you need the thresholds to go up and down with the time of year. And so this is one reason why you would have a Z depending on omega. On the other hand, if you were a marine biologist and you cared about the welfare of turtles or coral or fish, then the animal doesn't care whether it's summer or winter, it just cares how hot the water is. And so that's a case where you'd have a Z that is absolute, not depending on omega. Okay? So anyway, the theory I'm presenting, it doesn't require the observations or the thresholds to depend on omega, but they can or they may not. Okay, well, in a similar way, in the same way that extremes can generate targets, having targets and these random scale factors, they let the targets change significantly in shape and size from fiber to fiber, and this gives the same kind of flexibility to track these anomalous statistics. Stefano talked about, there he is over there, talked about economic data on Monday. So if you watch the news, sometimes they talk about unemployment rates and seasonally adjusted unemployment rates. So what they're doing there is they recognize there's a cycle and they adjust for that cycle. So it's a similar kind of thing. All right. Yes, so in extreme value theory, what you're interested in is you have your orbit of length n, and you want to know that you observed at least one extreme event in that orbit. Yeah. But just to reiterate, what we're doing here is we want to look at the counts of the numbers of extreme events in an orbit of length n. Not just did we have at least one, but how were those clusters distributed. So I'm just reiterating here, this is the random variable we had before to do the counts. Of course, I can swap out my target with my extreme event, and this would count the number of extreme events in a random orbit of length n. And again, to reiterate, we're interested in limits of these discrete distributions. If you're talking about a random extreme value law, then what you'd be interested in is the limiting value of seeing at least one extreme event, which would be the complement of, so 1 minus seeing no extreme events. Yeah? So maybe now you can see that an extreme value law is a kind of specialized version of what we're doing because we really want to get these distributions here in J. All right, so in the deterministic case, many people have looked at hitting times and extreme value theory, and I'm being a bit lazy by just listing up some names here, and I'm sorry if your name does not appear here and you worked on this, please let me know if that is the case. In the random setting, with the quenched random setting, there's not too much work, so some early work was looking at random subshifts, and they're looking at targets that are cylinders, and cylinders that were around periodic sequences. So this is similar to my second slide where I talked about geometric Poisson. And what they show in this case was, in fact, that you get a polyaptly limiting distribution. And then more recently, moving to Le Sauter-York type maps, there are some results that are similar to what I'm presenting today. All of these use an average T scaling, so they don't have this T omega that can adapt from fiber to fiber. Each of these requires some decay in the driving system, which we do not. So there are, and of course the technique is rather different. So there are, I don't want to say one is necessarily better, but there are some differences. So our techniques are spectral. So we see spectral techniques as very flexible. You have, what I will show you is a bunch of hypotheses on the operators. And if you can verify them for your map, then it's like a general purpose methodology that you can crank and get the result. Yeah, we don't have any mixing in the driving. We do need summable decay in the co-cycle of fiber maps, which I'll come to later. And yes, we have these random scalings. Okay, so now I want to talk about, I have one slide on related work with spectral methods. So Keller-Livrani, in a 2009 paper, they have a perturbation result that concerns operators of transfer type, where, okay, you have your operator, your spectrum has some leading real eigenvalue, and then you perturb the operator. And you want to know, how does that leading real eigenvalue change with respect to the perturbation size? So it's a derivative in the movement of the leading eigenvalue. And then using this result, Keller made a nice spectral approach to extreme value theory in the deterministic case. And so what we have done is follow a random version of this. So what would be a random version of this derivative? Well, you have a operator co-cycle from fiber to fiber. That operator co-cycle has a leading Lyapunov multiplier on each fiber. And now you perturb on a particular fiber, your operator, and you want to know, how does the leading multiplier vary with respect to the perturbation size? And so that was part of this recent paper. And then also in the same paper, we leveraged ideas from Keller 12 to make a spectral version of a random extreme value theory. Back in the deterministic case, for these hitting time distributions, Zhang used the Keller-Livrani deterministic theory to look at Gibbs Markov maps, Markov holes, hitting times to Markov holes, and he showed that you get a standard Poisson. So this is effectively what I showed you on the very first slide of the talk. You have an interval, a target around an aperiodic point, and you get simple Poisson. So this is a spectral approach to show that. But what I want to do today is go much further, and also in the random case. Okay, so here is our transfer operator co-cycle. It's just like the map co-cycle, but you put an L where there's a T. And I guess this is, again, reiterating with more notation what I had on my third or fourth slide. This is just saying you have a random thermodynamic formalism. So you have a random conformal measure, a random equivariant function, and these Lyapunov multipliers. So when you hit the omega phi with the omega L, you push it forward to the next phi, and you pick up a multiplier. When you hit the conformal measure, you pull it back to the previous fiber, and you get the multiplier. And you put the phi and the nu together in the usual way to get a mu, which is invariant for your dynamical system. Okay, now this is the perturbation. So we make a special kind of twisted operator, and it has two indices. So n, this is the level of the target size. So h is depending on n, and that's how small it is. And s is going to be an argument of a characteristic function that comes at the end of the slide. So what you do is the usual kind of twist thing. You multiply your argument f by e to the is indicator on the target. And then you just apply the usual operator. Okay, so we need for our Banach space here, we need the indicators on the targets to be in the space. We need the indicators to have bounded norm. This is my counting function again, except that I separated the n, which is my target level, from the k, which is how far I iterate. And what is nice about the twist, now you see what is nice about the twist, when you take k iterates along your random orbit, what you get is k iterates of the unperturbed operator applied to e to the is and then this capital S counting function. So that's one nice thing, but it becomes even nicer when you see that the characteristic function of z omega n, which is, I mean, just by definition, mu of this random variable, you get to mu e to the is s omega n. And so having this in here is going to be very convenient for taking the limit of the characteristic function. So the whole strategy, we're moving to characteristic functions. So what we want to do is prove that we want to show what is the limit of z omega n as n goes to infinity. So what we do is we take the characteristic function of the z omega n's. We show pointwise in S that we have a limit. Okay, so we have some limiting characteristic function, and then we will infer from that limiting characteristic function what is the limiting distribution that we converge to in distribution. So our goal actually for most of the talk is to determine this limit. Okay, so we need to consider also these perturbed cocycles. And so here are some hypotheses. So these operators have to be bounded, the unperturbed ones. This says we have a thermodynamic formalism for the perturbed operators. So it's the same kind of thing I had before. If you act on some f with your perturbed operator, then you project onto a one-dimensional space given by the phi, plus the rest, and the q is going to decay. So you project onto your top space and then the rest. And this top space, it has the same equivariant property that you would expect, and the nus here that do the projection, they have the same backward equivariance property, just as before. We also need that the twist is actually a small perturbation. And how do we say it's a small perturbation? Well, like this. So this is in the dual. So we would take the supremum over the unit ball in b omega, and this should go to 0 as n goes to infinity. This says that our twist is a small perturbation. This hypothesis is about decay of q. So you take the q here, you go n iterates, capital N iterates along your q cocycle, and you should decay like alpha of n, similarly for the twisted q, and the alpha of n should be some summable sequence. So this is the main decay hypothesis in the fibers. And then some technical limit exists and equals q omega k hat, which I'm not going to talk about until much, much later. All right, so this is our first main result. So the limit of these characteristic functions, which are omega dependent, they are characteristic functions of this counting distribution. The limit of these characteristic functions is given by some phi, which is omega independent. So when you take the n limit, okay, you lose the n, but you also lose the omega by ergodicity, essentially. Okay, so in more detail, you have your random perturbed system. So this is the base. These are your fibers in your domain. This is the map. This is the Banach space. This is the unperturbed operator, conformal measure, densities, and targets. All of these things have omegas. I just suppress the omegas. The limit of this characteristic function is, this is the definition of the characteristic function. So I go in two stages. So stage 1, I want to represent it in terms of multipliers. This is I guess, the spectral part. And then stage 2, then I want to represent it back in terms of things to do with the target. So you see there's a t here, which was the target scaling, and there's this theta, which is in terms of the q that I haven't told you about yet, but yeah. Okay, so what can we conclude from this then? We know that we have this limit of characteristic functions converging to this function phi, so then by Levy continuity, we know that this phi is a characteristic function of some distribution that the z omega n's converge to in distribution. That's what we know so far. We will know more as I go on, but that's what we can learn at this stage. Okay, so I'll spend a few slides now sketching how we get to 1 and 2. So first to 1. So for 1, all we need actually is this splitting and the decay. Okay, so here we are with our characteristic function. And then what you do is you plug in k iterates of the unperturbed operator. When you do that, what's going to happen is you push forward the nu. So the nu here was on omega, but now you push it forward. And you also have to compensate by dividing by k not copies, but a k product of your multipliers. Okay, then you look at this and you say, oh, but this is just my twisted operator iterated k times. That's very convenient. That's why we did it, actually. And now you use the splitting to go from here to here. So you're acting on the 1 function. So I can write it as I project onto the phi, and I have the rest with the q. I also pick up k multiples of the twisted multipliers. Then to go from here to here, the nu of the phi is 1 because we normalized it to be 1. And now we put k equal to n, we let n go to infinity, and what happens is the q is going to decay to 0, so this term goes away. And this term is close to 1, and in the limit it goes to 1. So all you're really left with is this quotient of products. So now we're at what I've shown is how we got to here. So currently we're at this stage, and now we want to go on to 2. And this is where the perturbation comes in. So now we need actually the perturbation theorem. So in this previous paper, we had the abstract derivative theorem for random cocycles that I talked about, and here I've translated it to the setting we're in today. So you have your random perturbed system. The s is the argument of your characteristic function. So for every s and almost every omega, you have this limit. So what this is talking about is the derivative of lambda naught, the leading multiplier, in the direction given by, so you have your leading, you have your operator, the unperturbed one. You're perturbing it in a direction given by the twist operator. And you want to know, how does the leading multiplier change? How does it change? Well, this is a derivative quotient. You have the unperturbed and the perturbed. And then here you have effectively these, you can interpret this as the size of the perturbation. The size of the perturbation is actually the measure of the target. So this is a 0 over 0. This is a derivative limit. And you get this expression here, which is in terms of the theta, which involved the q's that I didn't tell you about yet. Okay, so let's just say I have some large n here. So then, in that case, let's say what I had before is approximately the right-hand side. And then just rearrange things to just push things around, so then I have a quotient like this. And if you push things around to get a quotient here, this is what you get on the other side. Okay, then for first order target size, so your target is very small, then 1 minus this is exponential of this term. And then recall that the measure of the target is t omega on n, so we can plug that in here, and we're up to here. So it's getting, if you remember what the expression I'm aiming for is, it's already looking kind of close. I just copied that here. Now, what we have is an estimate for a quotient on a single fiber. But what I want is this. I want a quotient of products on many fibers. So that means running a random orbit and taking random products of this quotient, which would mean random products of this exponential, which would mean an exponential of a Birkhoff sum in omega. And then this Birkhoff sum you can show converges to what you would get from Birkhoff, the expectation of T omega theta omega. Okay, so now this expression on the right, that is what I had in the theorem before. Oops. That is what I had here. So now we reached 2. And in particular, so because of this expectation, it's independent of omega. Okay. Right. So now I want to argue that this is this Z, this limiting distribution, is compound Poisson. Okay, so we say that a random variable is compound Poisson if it's what is called infinitely divisible. So this means you can express it as some arbitrary sum of IID random variables. And in our case, our characteristic function is having this exponential form. And you can trivially put an n here and then divide by n. Actually, imagine this n is under the t. So you can represent your phi as n copies, a multiple of n copies of the same thing, except all I would have to do is just divide my scale factor by n. So you have your, what we've shown is you have your characteristic function. You may represent it as an n-fold product of the same things, and so therefore you have a characteristic function that is representing an IID sum. And therefore we're compound Poisson. So that's easy. Okay, if we want to get back to a mass distribution, we could use Levy inversion. So Levy inversion would just be, so if you want to know what is really the probability that Z is K, then you have this formula here. What goes here is your characteristic function, and this looks complicated because I just plugged in the phi expression here, but normally this would just be your phi. In principle, you can do this, but in practice, it's not so easy to get a closed form for this inversion. So instead, what we do is develop more explicit formulas for the means and variances of Zs and the components of Z. So that is what I'm going to do now. But before I do that, here's the slide with the Q. So that maybe we start at the bottom. Here's my Q. And the theta was, I already showed this before, this was the theta in terms of the Q. Okay, what is the Q omega K? Well, that's a limit of Q omega K n's. And what are the Q omega K n's? They are given in terms of sums of beta omega K n L's. And the beta omega K n L's, they are numbers between 0 and 1. And okay, so you see here, you take measures on the same fiber. The A here is a subset of this set below, so you're conditioning here, so this is a number between 0 and 1. Let me describe what the A is now. So what you do is you go back, this way, you go back to fiber K plus 1, minus K plus 1. You ask that you hit the target there. You have an orbit of length K. You ask that you also hit the target now. And then you want to hit the target L times in between. Okay, so you hit it at the beginning, at the end, and L times in between. And that is this set A NKL. N is remember the depth of the target. Okay, so well, if you figure out these measures, then you have the betas, and then you plug them in to get the Q hats, and then you take the limit, and so on, so on, so on. Okay, so in principle, in examples, you can compute these things if the example is easy enough. All right, now expressions for the mean and variance of this limiting Z. Okay, so the standard kind of thing you would do with characteristic functions is you can get moments with derivatives. So if you want the kth moment, then you have this relationship with the kth derivative of phi. And, okay, our phi contains the theta. If you remember the phi, it had exponentials, blah, 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 integral t omega, theta omega. So in order to differentiate it, the theta should be differentiable. And, well, this will depend on how the alphas decay. If they decay exponentially, then the theta is infinitely differentiable. We can differentiate as much as we like. For slower decay, you get less differentiability. So if this theta is twice differentiable, then we get that the expectation of z is the expectation of these scale factors. The variance of z is the expectation of the t's and this quantity sigma, which is given in terms of the betas. So if you want higher order moments, then the formulae get more complicated. We can also get finer information on the z using the fact that it's compound Poisson. So z is of this form. So you sum these IOD random variables where n is Poisson distributed. So n is a Poisson random variable. The Poisson parameter is given by the expectation of t and this quantity theta naught, which I didn't define yet, but is from this previous paper that looked at extremal value theory, and you can interpret this as a random extremal index. The x's, which are all identical, they have characteristic functions given by this expression, which involves the t's, the thetas, and the theta naughts. The characteristic function of z, phi, can be expressed in terms of the characteristic function of the x's, but this is just probability theory. This is not dynamics, that part. And the expectation of the x's, that's given in terms of the t's and the theta naughts, and the variance, or the second moments of the x's involve the t's, the sigmas, and the theta naughts. So in principle, we have explicit formulas for the means and variances of the z and its component x's. Okay, so I think I'm doing rather well with time, probably talking too fast. So what kind of maps can you verify the operator hypotheses for? Okay, so here's what we did in the paper. So interval maps, surjective, finite branched, expanding, monotone, non-singular, kind of nice but discontinuous. We need, we can use different potentials. So if you don't have the derivative potential, you need also upper and lower bounds on the potential. The co-cycle should be covering, so we need this for things like you want your phi's to be positive, and in examples you need to run a random perturbation theory that requires covering. The targets can do pretty much whatever they like. So in this case, we're talking about interval maps, and so targets would be things like unions of intervals, and that can vary wildly from fiber to fiber. It's just they all have to scale like 1 on n, but the actual sizes of them, the t omega can vary wildly from fiber to fiber, so that's quite general. And of course, we need our co-cycle to be quasi-compact. In this case, we're just using BV, and you can check that finitely for some map co-cycle. Okay, so this sounds somewhat general. The example I'm going to show you looks probably very simple, but that's because I want to firstly compute things and not have huge formulae. And secondly, also to show you that even with very simple situations, you can get rather complicated still hitting time distributions. Okay, so here's a map, a graph of an interval map, and the family, all you do is you just kind of vary the central slope. So they all share a fixed point at x is a half, and you just vary this central slope up or down. I drew it with linear branches, but actually it doesn't really matter what happens out here or here. You could have nonlinear branches, and it doesn't. The only thing that matters really is the derivative at this fixed point. The driving can be whatever you like. We don't need decay, so it could be something like a circle rotation. And then the targets, well, okay, in this case, they should be intervals around a half, and they should have measure, or in this case, diameter, like this. So T omega on n, you can also put in a little more wriggle room with a bit of an error that depends on omega and n, that lets you fit in a few more examples. Here my scaling function, I'm limiting how much it varies from fiber to fiber just to make the formulae shorter. So what this means is, let's say the minimum slope was 3. So then this condition would say, on adjacent fibers, you have to be having ratios between 1/3 and 3. Okay, so in this situation, we can compute all these beta, omega, n, k, l's, and they're all 0 unless L is K. So the situation here is that you have a fixed point, so when you come close, then it's rather likely that you keep hitting in an orbit of length K. So, I mean, in particular, you can't go away and then come back in less than K. So this lets us compute these Qs explicitly. And, okay, in this example, this is what we get. Our characteristic function has this explicit form. Everything is given here. The main variables are the t's, which are the scale factors, and the alphas, which are the inverse derivatives at the fixed point. So what do we know? We know that our hitting time distribution converges to compound Poisson. Here we have some infinite sum. There's no problem with it converging, but it's not a geometric sum in general. And so actually, this may not be the characteristic function of geometric Poisson or polyaply. And in fact, we don't know actually what, we didn't spend a huge amount of time thinking about it, but we don't know exactly what the characteristic function is in this case. Okay, well, let's make it a bit simpler. So let's fix the map, but keep the random targets. So let's just have one map, but the targets can vary from fiber to fiber. In that case, these alphas all become some single alpha. This product just becomes alpha to the k plus 1, and then you can do a geometric sum. You can do the sum, and this is what you get. And now you can look at this and say, oh, okay, this is now geometric Poisson. And everything is deterministic except for the expectation of the t's here. So your geometric Poisson with parameters given by this and this. All right, and last example, let's say you have 2 maps or n maps, and they're chosen IID. And let's say the scale factors, here I'm saying 2 scale factors, but actually you could have countably many or even uncountably many scale factors. They just have to be chosen independently of the maps. Okay, so then let's define some alpha bar. This is our average inverse slope. And T bar is your average scale factor. And then you can find that your limiting characteristic function is given purely in terms of the average scale factors and the average inverse slopes. And this is, of course, again, polyaply. If you want to see, in this case, you know what the mass distribution function is. There it is. And I will stop there. Thank you.